let's start the discussion. And I'm going to start it off by going back to a comment that Nicolas Bouché made about the H1 fluff, I think, above and below the disk, and I'll let him expound a bit upon this. It might not be dominant form of H1 around most galaxies, and he posted an image in a paper by Fabian Walter that showed you can have H1 column densities of 10 to the 19 out to, I think, 40 kiloparsecs in stacked H1 cubes around, along the radial disk, I think you mean. So, Nicola, why don't you talk about that a little bit more, and we can begin the discussion.
Yeah. So thanks, Ben. I think these co-rotating structures that Crystal showed, and I completely agree with the picture that she presented. They're not. You should not think about these as thin disks, but as really co-rotating structure, gas stuff flowing around and rotating in the same direction. And what we see with magnesium-2 is obviously cool from our CGM point of view, 10 to the 4K or so at 20 to 60 kiloparsec. And then I was stunned by these results of stacked H1 data cubes. And what they do is they remove the kinematics to do the stacking, such that they can get high signal to noise along the major axis, and find that the density profile, or the column density profile, extends out to 30 kiloparsecs or 40 in some cases, with column densities of 10 to the 19, which is more or less in agreement with the column density you would expect from the magnesium columns that we see, or that Crystal sees. And so this is kind of an emission picture of what's going on. And I was wondering then, in maybe it's to Filippo, I don't know if he's here, but in the amount of H1 that is extraplanar, it's surely there and it's surely happening, but it seems that to me there's a lot more mass in this co-rotating structure between 20 and 40 kiloparsec, given the column densities.
Yeah, that would be great. Filippo has his hand up, so please comment.
Yes. Okay. Yes. No, I was just yes, just because you mentioned that I could say something about it. So I think galaxies are I mean, the picture is that there is both. So these extraplanar layers, as far as we know, are in all galaxies. There is the Marasco et al. Paper that has been mentioned also by Crystal. Essentially, the whole sample shows extraplanar gas, and that the amount of gas that is there is of the order of 15% of the total mass of H1 in the galaxy, and maybe in the outer parts there is more. You can say that there may be twice as I don't know, 50% of the gas can be in the outer disks, or 30% or something like that. But there is a big difference. That the gas that is in the extraplanar layer, we know for sure that it cannot stay there, because it's not in equilibrium, any sort of equilibrium, and it's not in particular in vertical hydrostatic equilibrium. So that gas is going to come down to the disk, and that's why we think that it's continuously replenished by a fountain, but you can also replenish by an accretion if you want. But the problem is that the time scales for it to come to the disk are very short, are few times 10 to the 7. And the whole layer disappears. So if you have to keep there 10, 15% of the mass of H1 all the time, you need a big flow, and this is what is very easy to determine, that the flow to keep it there is actually larger than the star formation rate. While in the outer parts, okay, there may be some inflow, but also you have rotational support quite a bit.
Right. It's not clear to me how much inflow you have in these outer parts compared to the ones that are coming vertically. And also the vertical stuff that has to come down seems to be kind of doing a kind of quick back and forth, up and down above the disk from supernova feedback. And so from the perspective of the galaxy feeding in the bathtub context, it's you are simply reusing. So it's more like a recycling process where we really need to have a significant amount of accretion from the outside of the virial radius to sustain or to replenish the gas on timescales of a few gigayears.
Yeah, I mean, this, we go back to the usual discussion, but one thing, let me point out just this, Ben, and then I shut up, but I don't say anything else. And the galactic fountain model without accretion, so without the mixing and of the fountain gas with some material that is coming in somehow, does not reproduce the data, because you don't reproduce the kinematics of the extraplanar gas if only have a pure galactic fountain. We see clearly that the galactic fountain is interacting with something, and one interpretation is that it is interacting with accreting material and bringing it down to the disk.
Let's move on to Nir's question that he posted in the Slack.
Hi, thanks. This is really interesting. I've heard Chris Martin refer to the rotation signatures that he finds in the Lyman alpha halos he observes with KCWI as extended thin rotating disks. I wonder if this is primarily a difference in interpretation, or is there an actual redshift evolution to the structure of these rotating halos, since the ones that he's observing is at redshift 3 or above? And as kind of a corollary to that, I wonder if we could potentially distinguish observationally in the kinematic signatures between kind of a rotating cooling flow or things of the sort that we've been talking about versus in spiraling cold filament, which might be very narrow. Yeah, thanks.
Yeah, does Chris, do you want to respond to that?
Sure. Yeah, I was cautioned by Avishai not to call them disks, so I now call them extended rotating structures, which is sounds a lot like what Crystal was calling them.
Fair enough.
You cannot really, with the data, determine that they're flattened disks. They're consistent with, it could be a thick or a warped kind of structure with multiple planes, within a range, relatively tight range. But so come up with a better name.
I think we definitely want to talk about the morphology of this extended thick discs, and it's great that we have Stephanie Ho on the panel. I do see a panel member, another panel member with his hand raised, and that's Zach. So I will give him the floor.
Okay, I can talk a little bit about, from a cosmological simulation perspective, what we would naively expect to see, and just kind of give a brief outline, both as a function of redshift and as a function of halo mass. So for a constant halo mass across different redshifts, as you go to higher redshifts, you're going to expect thicker, more dense filaments, etc. And what that means is that you can see more of the infalling material is going to be in the form of filaments, which means it will be less coherent potentially. Instead, if it's coming from say, accretion out of a hot halo onto a disk or something of that sort, which is actually kind of what Duchan, well, what I've been looking at and what we see in some simulations, then that will be more organized and coherent as it happens. Now, that's also the case for when you look at change between halo mass. So if you go to a Milky Way mass progenitor and look at low redshift, then at low redshift, most of the cool gas that's forming in the inner region is accreting out of the hot halo. and is therefore going to be aligned with the disk because it had time to exchange angular momentum. If you go to pre-virialization, then this gas is going to be supersonic and can be falling in with a variety of directions and be therefore much less coherent. And so then you'll expect a messier disk at that time. And so you'd overall see this kind of change in coherence as a function of both redshift and halo mass. That would be my general predictions. I don't know if that's consistent with what others expect to see.
Yeah, interesting. Nicolas, go ahead. I see your hand raised again.
Just to comment on the morphology and Near's question here, we would love, I think, to image these co-rotating structures we see with the metal lines at redshift 1 or 0.2 like crystal in laminar alpha. That's currently not possible. And vice versa, at redshift 2, we would love to do the same experiment with magnesium 2. And that's difficult. So it's difficult to compare these two things because we're not really necessarily probing the same gas. With Muse, there's also a lot of laminar alpha halos around quasars or around galaxies. And these tend to be, on the majority of the case, spherically symmetric. There's not a lot of evidence for coplanar gas seen in laminar alpha emission. That would be the analogs of the magnesium 2 co-rotating gas at redshift 2.
Interesting. I want to talk about, I want to make this conversation active. There's a lot to digest here. And I want people to think about, the morphology of thick disks at different redshifts and around different halo masses. And I thought, Crystal's highlighting of the work of Stephanie Ho's looking at those Eagle simulations was really interesting, and the issue of contamination. But let's shift the conversation to outflows. In some of Stephanie's stacks of Eagle galaxies, you saw the gas along the semi-major axis, but you didn't see a lot of gas out of the semi-minor axis of outflows. And I know Nicolas has observed this, and Glenn, and all these people. So, Jess, I think you had a question about this. Do you want to talk about signatures of outflows, where you see that, and then we'll let the other observers chime in.
Oh, well, I think I have heard some conflicting views in particular on the kind of like azimuthal, dependence of magnesium 2 absorption. And so since so many people are here who study this kind of thing, I would really just love the key players, including Stephanie, Hsiao-Wen, Nicolas, Bouché, and Rongman if he's here, to just weigh in on, the azimuthal dependence of these absorbers, weak and strong, because I guess there's some kind of conflict.
Yeah, because if observers don't raise their hands soon, I'm going to talk about, that Eagle, I don't think gets the magnesium 2 above and below the plane in the outflows, right? And I think other simulations probably don't get it either. Though I think there is some work. So we'll go with Nicolas again and wait for others to chime in on the observational side.
Yes, I'll talk about the simulation side actually, because I was part of the De Filippis paper that in TNG that Crystal mentioned. And there as well, there's no magnesium 2 in the minor axis. So the bimodal distribution is not there. We only see magnesium 2 phase gas in the co-rotating structure around the disk. So that's in simulation. That seems to be a general feature currently, that we got the disks right, we get disk formation, but in terms of the outflows, there's something missing. And in terms of the controversy, I think it's non-controversy, but I'd like Hsiao-Wen to speak first.
We're going to put people on the panel on the spot. So Hsiao-Wen, take it away.
Well, I think it would be good to review all the observational results. I don't think if you put all the papers together, the picture is that clear. I mean, starting out, it's great that Rockman is here as well. His classic 2011 paper showed very clearly the enhancement in magnesium 2 line width within 50 kpc along the minor axis from these redshift 1-ish galaxies. But there was, at the same time, there's no distinction beyond the 50 kpc radius. And since then, there have been a lot of papers, trying to look at the similar trend or lack of along the same direction. And I have seen literally from, left and right that says either there's such bimodality all the way out beyond the 100 kpc, or there's no such azimuthal dependence. And also, it involves work from, like what Crystal mentioned, very careful analysis of highly resolved, spatially resolved galaxy morphology, either from HST or from ground-based adaptive optics image. To measurements based on seeing limited data. Having done this myself, I just find a clear definition of inclination and orientation is not straightforward. So I don't know if it's worthwhile just do a very careful aero budget analysis. And just to see, I see that there's the contest about metallicity measurement. Maybe there should be a contest about, even same image, same galaxy images, do different observers produce the same alignment, inclination and position angle measurements. I think that's something that's worth considering. But I think, Jess is also aware of all these papers I was referring to. I think most of us really could not get a clear picture of, whether or not there's really a smoking gun observation that tells us concretely that one is, outflows or infall. It's just what I think.
I feel like Crystal probably has a very different view, but I don't know. I'm not, yeah, I think it's interesting to hear you say that it's not a simple picture, because that's definitely the impression that I get. And I was hoping that there was. There's a lot of people now with their hands up, so I'm really interested in hearing this.
All right.
You guys successfully induced discussion.
Thank you, Hsiao-Wen. You have inspired a lot of interaction here. Let's give it to Crystal. She's our keynote. Let's give her the floor.
I felt like I'd already had my turn to speak there, but I was kind of invited there by Jess. Just looking at the simulations, right, on a individual galaxy by galaxy basis, this co-rotating gas is a bit of a train wreck, right? I mean, it's a rotating structure with filaments and arms and things coming in and out, and some of that gas is counter-rotating. It's just that on average, right, in a median stack, there is very much a net co-rotation. But any individual galaxy, any one sightline, there's all kinds of results you could get. So we're talking about mean properties here, and bulk structure and bulk motion. So I think you've got to keep that in mind when you go and analyze real observations, right? It's what you get in the mean that we're after. I think the Lan and Mo work, where you've got 500,000 galaxies, really shows that statistically, right, in a minor axis sightline, you will get a higher magnesium 2 equivalent width than you will at a random azimuthal angle. I mean, with those kind of statistics, I don't see where that result is debatable. We can argue about what that equivalent width excess means. I think we would all agree it's got to do with kinematics in some form. Now, if you're going to push a step further and say, is that a wind? I think things become more debatable, even what you mean by winds. If I had gone further, I would have showed one system where there's a down the barrel observation of magnesium-2 and a transverse sightline detection of magnesium-2. And I'm a co-author on the paper, so I can say that we probably incorrectly model that, as gas clouds coming out of the starburst and traveling 60 kiloparsecs into the halo. That's completely incompatible with the present wind models. It's different gas. It's maybe different phases of the same wind. It's maybe two different ejection episodes that we've connected. So what's clear to me is that the CGM above, i.e. along the minor axis of star-forming galaxies, is kinematically disturbed.
I see
Seems likely that has something to do with winds.
I see Rogman's hand up, and his name has come up a lot. So Rogman, take it away.
All right, thank you. Can you all hear me? So I think I really echo Crystal's statement. I think she very eloquently put it, that with statistical force, at least my paper, we had stacking analysis of thousands of foreground background galaxy pairs. I had HST imaging, and I spent, I don't know, months staring at individual images to make sure orientation angles are correct, etc. And we were very careful, because this was the first study, to make sure we only included isolated inclined objects, etc. And the statement is, when you do this kind of a stacking analysis in bins, although you might have errors on individual measurements, when you bin them together, on average, there seems to be an enhancement of magnesium to equivalent width along the minor axis compared to major axis. Now, is it completely not consistent with the bimodal distribution that Nicolas finds and Glenn Kapczak's group find? We spend a lot of time thinking about it. We modeled it. We had a lot of interaction back and forth with them, and we agreed that they're not inconsistent, simply because when you stack, there are two components coming into play. You have contribution from equivalent width itself, which is perhaps due to column density, perhaps due to kinematics. For a second, just leave it aside. B, which is very important, is also covering fraction. If you have excess extended disk, you are more likely to have strong absorption along the major axis at a very small sort of azimuthal angle. So if you have a bunch of sightlines around it, you're more likely to have an average value, which is sort of depressed down by non-detections in those sightlines also, if you have a sort of a finite size of the disk. So when you have an average measurement like my work or Lan and Mo's work, even the model suggests that you should have this kind of a excess along the minor axis and slight depreciation along the major axis, simply because of this weighting. Whereas if you do individual sightline study, clearly if you have a DLA along the major axis, you probably should have a whopping magnesium-2 absorption, which is clearly what we see in individual sightline studies. So I don't think they're inconsistent. It is, I agree, it is a little bit hard to interpret, but that's why I think we did spend a lot of time thinking about it, and the conclusion was that these two results are consistent. And again, Crystal's point, the result she showed is very, very sort of, let me just finish. I think the result she showed is very, very informative, that you have very, very uber strong magnesium-2 absorbers, equivalent width of 2 or higher, etc., along the major axis. This is what you would expect for DLA-like sightlines. And the stronger sightlines, she shows that, along the minor axis, there's a strong contribution. So that's the picture I have in mind. And the weaker sort of non-detection or weaker absorbers, they could be anywhere. So I'm not, again, making a statement that this is definitely due to wind or this is definitely due to something else, but I'm saying there is a signature of excess absorption in these studies. That is definitely, I would argue.
So if I could just a direct response to the point both Crystal and Rockman are making. So thanks, Rockman, for highlighting the caveat in interpreting the stacked spectra, because the mean equivalent width really is a combination of the actual intrinsic width and the covering fraction in the volume we are trying to probe. So I just want to step back and think about this. Once we have that idea in mind, that the mean equivalent width is folded in the differential covering fraction. That means the implication will be that along the minor axis of, say, red galaxies in LAN-MO result, means that it's quite likely that even for red galaxies, along the minor axis, we do see sometimes strong magnesium-2 absorbers, possibly stronger than star-forming galaxies. What does that tell us? What does that mean? I think that's a question I haven't heard the answer to. Once now we recognize the fact that the covering fraction is not unity. But another point, maybe I should come back to about the velocity shear. If I'm gonna stop here.
Okay, I'd like to hear about that at some point. Too, I think there's a lot of, we want to go up, to LRGs and more massive halos at some point. And I see Nicolas' hand up, and I'm gonna yield the floor to him.
Yeah, thank you, Ben. I wanted to add my 2 cents to the debate here about, and we have to distinguish between whether the CGM from magnesium-2 is isotropic or not, and the interpretation. And Crystal said that nicely. I think Jess's question is like, is the CGM from magnesium-2 sightlines isotropic or not isotropic? I think the evidence here is quite strong for not isotropic distribution of the metals in low redshift galaxies, redshift 1 or so. There's a number of studies, independent studies, including the one from Britt Lundgren that appeared today or a few days ago on AstroPH. There's the stack from Rongmon and other stuff. In my personal case, I was involved in 3 different samples and we found the same results. And it comes down that you have to be careful when you associate absorber and galaxy to make that connection. Typically, you have to take isolated galaxies and not having too many neighbors within 100 kiloparsec. On the point of seeing limited data, Ramon mentioned that it can be done with HST complementary observations, but with MUSE or IFU observations, you have the kinematic axis, and so it's very difficult to make an error for that. The kinematic axis for the rotation curve is what it is. So it's very difficult to make an error for that. And the other point I wanted to make is that we find with IFU observations with MUSE that, especially when you want to associate star-forming galaxies and absorbers, that O2 emitters typically do not necessarily have a continuum counterpart. About 30% of them don't have continuum counterparts to the depth of medium deep MUSE observations, which reached like 26 or 25 magnitude. And so when you do this observer galaxy pair business and want to try to study the geometry of the CGM, and you might have a different answer whether you have an emission selected sample or a continuum based selected sample. And then the question I have to Jess, because I don't see this as a debate, I can see many reasons why you would make mistakes and we have error in the measurements of the geometry, the alpha, all these errors would kind of wash out any kind of non-isotropic signal. This bimodal distribution would disappear. So how do we get this by accident in several different samples?
Yeah.
Just quickly, I think, yeah, it's great. Thank you for mentioning Britt. I don't know if she's still online. So the paper came out on the archive today, so I had the chance to just quickly browse through the paper. It looks like they are actually finding, I would say, a dearth of magnesium-2 along the minor axis. If you look at their azimuthal distribution, there's the sort of a peak at about 60 degrees, and another one coming in at about 0 degree along the major axis. So I think that just adds to this picture that's just further creating ambiguity in the whole.
I have to explain this because it's exactly what we see, and it's naturally explained in the biconical outflow, where the magnesium would be probing more the sort of the edges of the outflow, in line with what the picture of Tim Heckman showed last week. So this is at 90 degrees, you don't actually expect to have a maximum. It's more like at 60 to 70 degrees.
Okay.
So it's exactly what you would expect for an outflow scenario. Whether that's the right interpretation, that's a different question.
Well, let's have this conversation extend on, especially on the Slack as well. I see Stephanie's hand up, and she is a panel member, so I definitely am looking forward to hearing from her.
Well, I actually want to ask Nicolas of what he just said about the IFU, seeing limited data with IFU plus kinematic information for modeling the galaxy morphology to define inclination angle, azimuthal angle. So I'm just curious how certain because you have the two kinds of information together, what are the uncertainties of the inclination angle, azimuthal angle for let's say redshift 0.5 galaxies or megaflow redshift 1 galaxies? What are the error budget for those measurements?
So for the very good question. So for the major axis, the kinematic major axis is hard to get. You have a plus or minus sign of the rotation, hard to miss. So the major axis angle would be typically of less than 5 degrees error. On the inclination, we have done some tests on field. So we have the HST imaging, and we find that we can recover the inclination to 10 degrees. Actually, the standard deviation is 7 degrees on the inclination, and that's because we're doing forward modeling with an advanced algorithm. So it's more than just taking at the seeing limited data. We can take that into account to get the inclination.
I think there might be a comment by Joe about an isotropic outflow. Joe?
Yeah, I just wanted to say, we recently mapped in magnesium-2 emission. It's definitely an outflow extending about 20 kiloparsecs from a galaxy, and it's definitely not collimated. And so, the best we can model, it is isotropic. So, I don't know if this generalizes to the greater argument about statistics and whether, these enhancement of absorbers along the minor axis is actually tracing an outflow. But if this object, it's one object, but, if you were to extrapolate, it would not lead to such a scenario being a smoking gun, certainly for outflows, biconical outflows, that is.
That's great. We're talking about emission here and seeing a more isotopic outflow. Zach, you have your hand up.
Yeah, so I actually want to follow up on Joe's point, which is one thing. So I'm curious to hear, Joe, whether or not that was for a low mass or high mass galaxy, relatively speaking to Milky Way mass, because one thing that's really useful to think of, in my opinion, for the orientation of the outflows is whether or not we're talking about a disk galaxy or we're talking about something that is much more spherical, which has been kind of in the background of this discussion the entire time. So when you have something that's much more spherical, oftentimes you're not going to have nearly as much of an organized outflow, at least in simulations. Yeah, so I don't know. And Joe, was that what was the morphology of that galaxy?
It's lower mass, it's disky, but it's potentially undergoing a merger.
Okay, that's interesting. I want to get to a comment by or a question by Todd Tripp, and I'm going to read it off the Slack. It seems clear there is an enhancement along the minor axis of magnesium-2, but since this is Galaxy Evolution Week, perhaps we should tackle this question. Are those MG2 absorbers revealing massive outflows, or are they just metal-rich bits of smoke that don't carry much mass? And I think that's a great question. And Rogman loves that question. He's applauding it, so maybe he wants to answer that.
Oh, I got volunteered. I would love to know the panelists' view on it, because to me it's not that clear. There is a signature, which I actually do believe there is a signature, at least for let's take out crazy merger or starburst galaxies, regular star-forming galaxies. There is a signature of enhanced kinematics. That's my understanding of the literature review anyhow in this field, along the minor axis. At least up to some level, it must be tracing, perhaps entrained gas in an outflowing gas, or somehow clouds trapped there. But I don't have more than a gut feeling, I would argue, or from simple toy models suggest that this is reasonable. But that's all I have to add to that. I would love to hear from other people.
I'm going to yield the floor to Stephanie, because we haven't heard from her as much.
I guess my simple view of those like broad like magnesium 2 absorption along minor axis, I would more think of it as like kinematic disturbance, the range, like this velocity range spent by the magnesium 2 absorption, instead of thinking it as like there's a huge like mass like that like shooting out of the galaxy. I think like, for example, in the paper, like Crystal, like the first author of like 2019, that we did spend a paragraph or so like discussing this scenario and do some modeling of like, if you have like an outflows from the galaxy and we know which way the galaxy disk is tilted, and then like how can we model at least the range spent by the magnesium 2 absorptions. So I guess what I'm saying is just that like even having like broad like magnesium 2 absorption near the galaxy minor axis, it basically just at least for me in my view, just a signal for like kinematic disturbance from the wind materials.
I know that, I mean, if we, in the X-ray community, they do see bipolar outflows extending above and below the disk. But I mean, besides M82, of course, in more massive objects. But I don't think those go very far. So I was wondering if, evidence for outflows along the minor axis in other wavelengths, if anyone has comments on that. Because I know that they're seen in simulations. I saw Tim. Tim, do you want to speak up on that? Obviously.
Sure, yeah. I mean, I think you're absolutely right that most of the data where you can see clear bipolarity is at relatively small radii. I mean, maybe 10 kiloparsecs, something like that. And I think if this initial collimation is probably from the interstellar medium of the galaxy, and once it gets out into the halo, it's not obvious to me that this doesn't just in the end inflate a sort of big bubble rather than being more like a jet or something like that. So I don't find it surprising that you might lose memory of the collimation once you get more than a few tens of kiloparsecs, maybe 50 kiloparsecs out from the center. The other point I was going to make with the data that Joe was talking about, when I look at the image, clearly it doesn't look spherically symmetric, and it also looks like it's barely resolved in terms of the point spread function. So it would be interesting to see what this looked like in an HST image, is all I'm saying.
Also, magnesium 2 emission is backscattered in the wind, so that also might complicate things a little bit of how the geometry will look like.
Excellent point.
Yeah, and I mean, I think if I were to kind of synthesize this discussion, it seems like the evidence for bipolarity in magnesium 2 at least is really confined to, like I said, maybe 50 kiloparsecs, something like that. It's not, I don't think there's compelling evidence that this goes all the way up to the Wheeler radius.
Well, I'll bring it back to the Milky Way. I mean, we see these E Rosita bubbles, and they're extending at least 10 kiloparsecs up, but that's not 50 kiloparsecs. Do we see things like E Rosita bubbles, Fermi bubbles around other galaxies? And are they bipolar? And where do they lose their bipolarity?
I mean, I could just chime in. I mean, I think the largest outflow that I'm aware of that's clearly bipolar is this thing I showed in my talk that goes out to about 40 kpc. That's something that's sort of like a 10x ARP220 sort of starburst. So it, you know, it's incredibly unusual, but that's clearly asymmetric, and the bubbles that you see in oxygen 2 emission go out about 40 or 50 kiloparsecs.
Yeah, I'm thinking of like there's two examples I can think of, and I can't remember their object name. There's Edmund Hodges-Cook had this NGC object that had, you know, going out to 60 kiloparsecs in a kind of a classic X shape.
Yep.
And David Rupke has, I think, what's a Nature paper?
Yeah, no, that was the one I was referring to, was Rupke's paper. Yep.
Yep. Is that local? I can't remember, or is that higher redshift?
I think it's redshift of something like a half, my recollection.
Pretty local. Low redshift, I would call that. Great. Well, this lively discussion. We have about 5 minutes left, and I see Todd had a comment. Let's connect this to future observations. What are the best future or even current observatories for probing actual mass and outflows? And I'm going to leave this open to anyone who, you don't have to raise your hand.
You're talking about on the scale of the CGM.
Yes.
Yeah. I mean, I think the problem is partly that you don't even know the sign of the velocity that you're seeing, right? And these quasar skewers, it's hard to even know what you're seeing. That's interpreting the Doppler shift in terms of a, you know, going in or going out or going, yeah. And I think probably, I mean, some of the, maybe Jess could comment. I mean, you have, as we have estimates sort of at the order of magnitude level, I guess, of the total baryonic mass in the CGM. So you could come up with outflow rates if you made the assumption that you're seeing pure infall or outflow, but that's probably not a very terribly convincing argument.
I wouldn't want to do that, certainly. Yeah, I think for distinguishing between inflows and outflows, and mass estimates, I think, you know, you need kind of a combination of what Crystal, you know, has been talking about with these kind of like detailed galaxy data, right? Knowing which way it's inclined, which way it's rotating, which way it was rotating toward you, combined with high resolution absorption measurements, combined with emission measurements, then you might actually be able to say something about inflow, outflow, and mass in both of those flows.
Yeah. Hsiao-Wen, go ahead.
Was Tim gonna say something? Anyway,
Before, yeah.
I thought this is a great segue to next week about future observations. Going back to one of the points I was trying to raise earlier is about, you know, just looking at line of sight velocity shear. There's, especially with a pencil beam survey, while we do our best to measure the rotation curve, spatially resolved rotation curve within the star-forming disk, when it comes to the connection to a pencil beam detection at some 50, 80 kpc away, there's always non-negligible ambiguity there, especially, you know, talking to theorists. What I have been reminded time and time again is when they look into the simulation, even if you match gas and the galaxy at zero velocity with zero velocity difference, you may be looking at things that are megaparsecs apart when you actually look into the simulation. So I just want to remind people that we do have that kind of ambiguity in all of the studies so far, including the co-rotation measurements, but that could be resolved once we have the spatially you know, resolved observations in emission that's afforded by integral field unit data. I know, H1 radio observers have been doing this for ages, but we are really entering in the optical and hopefully UV regime into this new era that we can really combine spatial information with line of sight velocity information to unambiguously sort out the different gas motions that we are trying to understand. That's my 2 cents.
Yeah. Thank you, Hsiao-Wen. I see Tim's hand still up. If he can speak up, I think talking segueing into next week is going to be really lead to some very active discussions, and I'm very excited about having that IFU data, not just in optical and UV, but X-ray as well. Thinking about spatially resolving things and being able to detect velocities of gas at several hundred kilometers per second and below is going to transform our CGM field. So if it's now on the hour, it's 10 o'clock Pacific time, and that was an active panel discussion, and it will lead to more discussions on the Slack, which I highly recommend continuing that discussion. So we are going to we're going to end today's session, but look at the announcements and the general channel for Joe. I believe you are in half an hour, your after party, and then Nick will have one an hour later. Is that correct?
That's correct.
Okay. Thank you all, and see you at the after parties.
Thank you.
Thanks, panel. That was very nice, and thanks.
Thanks, and Jess.
Thanks, Ben, for
and most of all, thank you, Crystal. Really excellent.